Welcome back to our online classes. Today we are going to look at column resolutions and some exercises. So now, during separation in chromatography, the aim is to have a better separation between solutes in the mixture, such that if, for example, this is our solute A, so that you have a peak, for example, that can look like this. This is a proper separation. So this is a proper separation. But if you have a peak, let's say this is your chromatogram, and let's say you have something like this. Now this is not separation, this is not a proper separation, so it means that something needs to be done in that case. However, any good separation should have a good column resolution, so it means that the ability of the column to separate two solutes from each other, and not only separating but to have a proper separations and efficiency that's going to give us a better baselines. So let's look at, for example, there's an exercise here which is going to help us to flashback what you have done. A chromatogram has been provided, and the chromatogram of 4 different species A, B, C, and D, and the length of the column is 30 centimeter. And remember, we have the retention time for each peak and also the width of the peak base of each peak, and we also have the non-retained species, their time. Remember, we said non-retained species, this is the time the species that did not interact with the stationary phase took to move from point A until they were detected in the detector. So let's read. The question says a chromatogram of a mixture of species A, B, and C. A, B, C, and D provided the following data. So there's the data. Calculate M, the number of plates from each peak. So we have peak A, B, and C. We'll go straight. Remember, we said that number of theoretical plates for A will be 16 into retention time of, so into retention time of A over width of A squared. Okay, so that's gonna give us 16 into retention time for A is 5.4 divided by the corresponding width, which is 0.41 squared, and that's gonna give us, let's quickly calculate. So we have 16, it's gonna give us 2775 so that is for NA. And if we are to calculate for NB, we are still going to do the same. So it will be 16 into retention time for B is 13.3 divided by the corresponding width peak, which is 1.07, and everything gets squared. So and only replace here, and it's going to give us 247.0. So this is for NA and this is for NB, and let's calculate for NC. So NC is still gonna do the same. For NC is going to be 14. 16 into 14.1 divided by 1.16, everything here squared, and that's gonna give us, so 64.0, and plus ND, the last one, that is going to be 16. So ND is going to be 16. Retention time for D is 21.6, and the corresponding width is 1.72, and everything squared, and that's gonna give us 23.3. So that's how we calculate the number of plates from each peak. So the number of plates for each peak in this case is 16 into the retention time of that specific peak divided by the width of that peak, and everything is squared, and that's gonna give you the peak for each and everything. Then the plate height for the column. So remember here we have been told the number of plates from each peak. So this is for plate A, plate B, plate C, and plate D. And the next question is saying the plate height for the column. So remember how we get the plate height. Remember, n, number of theoretical plates, equal to length divided by plate height. So it means that the plate height is equal to L over n, and length, yes, is given to be 30. It's going to be 30 centimeter, and n will be the average of this. So you have 25. If you find the average, it's going to give you 25, 3, 4, and then you are going to divide it here, 25, 3, 4, and then that's going to make our h to be 0.01184 centimeter. So this is the height of the plate height for the column. So this is how we calculate the number of plate. We calculate the plate height first. If you have different peaks, you are going to calculate the number of plate of each peak. Then you find the average of all the number of plates. Then from there you are going to say plate height is equal to length divided by number of theoretical plates, and then you divide and you get the plate height. So let's write it somewhere here. So our number of theoretical plates is equal to 2534, and our h we have calculated to be 0.01184 centimeter. The next question says the resolution B and C. So normally when we calculate the resolution, we have to compare to analyze. Remember we said column resolution is the quantitative measure of the column to separate two solids A and B, or X and Y. So that is why we can calculate for the resolution of two components. Like in this case, we can calculate for B and C. And column resolution, which is denoted by RS, will be 2 into the retention time of T of RB, or in this case is C, so it's going to be T of RC minus retention time of B divided by the width of B plus width of C. Once we have done this, we can then substitute and then say 2 into retention time of C is 14.1 minus retention time of B, which is 13.3, and everything divided by width of B, which is 1.07 plus width of C, which is 1.16, and that's going to give us a value of 7175. So this is the column resolution B and C. You can do even for B and A, and even D and C, even between C and A, and even D and B, you can do that. So that's how we calculate the column resolution in part C. So let's look at So let's look at the length of column necessary to separate the two species with a resolution of 1.5. The length of column necessary to separate the two species with a resolution of 1.5. So in this case, remember, we normally say that the resolution is directly proportional to the square root of length. And then if that's the case, then we can say resolution of 1 over resolution of 2, then it's going to give us the square root. We can just do everything of L1 divided by L2, and in this case the resolution 1 we got was the one that we get in part C, and if I remember well, it was 0.7175 5, and the resolution for 2 is the one that you have been given here, and length 1 is the one that we add the length of the column initially, which is 30 centimeters. So we need to get the second length that can give us a resolution of 1.5. From there we can substitute straight 0.7175 over 1.5 is equal to square root of L1, which is 30 over L2 over L2, and from here we can square both sides. We can square both sides, and that's going to give us our L2 to be 30 times square of 1.5 over 0.717 squared, and that's going to give us a value of, so we have 131 centimeter. So our length 2 is equal to 131 centimeter. So the first thing that you need to understand is that the resolution of a column is directly proportional to the square root of the space of that length. So if you have resolution 1, it will of a specific length, and if you have a second resolution, it will give you of another length. And you can see when we have the length of the column, right, which is 30 centimeter, it gave us 0.7175 resolution. But now a perfect resolution is between 1 to 5, especially 1.5. Is a good resolution. So it means that the separation was good. And when the separation is good, what does it tell us? The length of the column has to be bigger. And you can see with the length of 131 centimeter, we are getting a better column resolution. So that's how we calculate the resolution, or the length of the column in regard to the second resolution. So part D is done. Let's look at part E. The time required to separate the two species on the column in part C, given that the length of the column is 30 centimeter. So what we are going to do, retention time TR1, and we have our TR2 versus length 1 and length 2. So we calculate the time required to separate the two species on the column in part C. And in part C, the resolution that we needed here between B and C gave us a maximum time of 14.1. So our retention time here for RT1 is 14.1, while length 1 of the column is given to be 30 centimeter, and length 2 we calculated, we got it to be 131 centimeter. So we are looking for the second time, retention time 2. That's going to give us the separation that will correspond to separation that give us 131, that can take place, or retention time within a length corresponding to 131 centimeter. So in this case, we know our retention time TR1 over TR2 will correspond to length 1 over length 2. It's directly proportional to the time. Remember, if the length of the column is longer, then the retention time is also going to be long. So now let's see if retention time if TR1 is 14.1 centimeter, 14.1 minutes, and we have 30 seconds. Do you think that for 31 centimeter in second column is going to give us a lesser retention time or a bigger retention time? It should give us a bigger retention time or a larger retention time. And from here we can just simply cross multiply and say TR2 times L1 is equal to TR1 times L2, and because we need TR2, we can divide both sides by L1. So our TR2 is going to be TR1 times the ratio of L2 over L1, and L2 we got to be L2. What was the L2? It was 131. Yeah, it's here. 131 divided by L1, which was 30, and this everything multiplied by TR1, which is 14.1, which is times 14.1. And if we punch that in the calculator, so we have approximately 62 minutes. So you can see that the longer the column length, the more time an analyte spent within the column, and the shorter the length of the column, the shorter the analyte spent within the column. So you can clearly see that the longer the length of the column, the more the analyte will be retained, and the shorter the length of the column, the less time the analyte will spend within that column. So that's how you can attempt these questions. That column resolution just help us to get the best separation or the best chromatograms, the best peak with a good baseline. So now optimizing column resolution simply means that what can we do to ensure that we achieve proper separation? Now, there are a lot of things that we can do. One of them is to, let me take the pen. One of them is variation in plate height. We have seen that now number of plate height is equal to length of the column divided by the, theoretical plate is equal to length of the column divided by the plate height. So it means that if we have a small plate height, we are going to have high number of theoretical plates, which corresponds to a longer length of column, and we are going to have a proper separations. So we can optimize column resolutions by varying the plate height such that if we minimize the plate height, so if we minimize the plate height, meaning that the number of theoretical plates is going to go high, and we can have proper or column resolution. So the question is, how can we then minimize edge? Which ways can we use to minimize edge? To minimize edge, we can do a lot of things. One, we can reduce the particle size of the packing materials. We can also reduce the diameter of the column, and we can also reduce the thickness of the liquid film. In our last class, in the video that we posted before this, in part A, reducing the particle size of the packing materials, that one normally happens with the column or packed column. If you remember, with the packed column, we are going to reduce the particle size of the packing material such that instead of having this bigger packing material, we are going to have smaller packing materials. This bigger packing materials is going to contribute to multiple path terms in the Van Diemter equation, if you guys remember, A, multiple path terms or eddy diffusion. So we need to minimize this particle size into a smaller particle size in in the packed columns. Okay, so we need to minimize the size of the packing materials to prevent eddy diffusion, and by preventing eddy diffusion, we are reducing band broadening, and when we reduce band broadening, we are just improving column efficiency, that is column resolution. The diameter of the column, so we need to reduce also the diameter of the column, especially for column chromatography. So if this is the column that we have, if we have a bigger column diameter, it means that we are going to allow longitudinal diffusions to take place a lot. And when we have longitudinal diffusions taking place, or prominent longitudinal diffusions, we are going to have band broadening, which is going to lower column efficiency. So what we need to do, we need to reduce the size of the diameter of this column into a smaller diameter so that we can minimize longitudinal diffusions. Minimizing longitudinal diffusion is going to help us to achieve high efficiency through column resolution. So we are going to have high column resolutions. And the thickness of the liquid film, remember also we talked about the SCSU term, the mass transfer term into the stationary phase and outside the stationary phase. So with the thickness of the liquid film, we need to make sure that if it is big or thick, we need to make it thinner such that in terms of the mass transfer term, our analyte will spend less time into the thin film or in the thin film or in the liquid film, especially the stationary phase. If it is very thin, it's going to spend less time to get in and come out, unlike when it is large or thicker, it's going to spend more time. Spending more time is going to create band broadening, which is going to lower column efficiency. And also we can optimize the flow rate of the mobile phase. Optimizing flow rate of the mobile phase, we realized yesterday that if we have a faster flow rate, it means that our mobile phase will move faster. And when it moves faster, we are going to have improper separation, because now you just put the analytes at the start, you just inject them, and in a few minutes they are gone, they are eluted. We are not going to have a sufficient time for separation. But if you have too or slower flow rate, also you are going to allow eddy diffusion to longitudinal diffusion to take place. So what we need to do is to have a moderate flow rate. That's when we say we can optimize the flow rate of the mobile phase. We need to make it moderate such that it is not too slow to lag behind the analytes, and it should not be too fast to make sure to allow improper separation. So the variation in plate height can help us also to optimize column resolution. So let's look at something else that you can do, variation in the retention factor. What is the retention factor? We looked yesterday that retention factor is just the ratio of time a solute can spend in the stationary phase compared to the time it can spend in the mobile phase. So for gaseous mobile phases, change the temperature. For liquid mobile phase, you can change the solvent system. So why do we need to change temperature for gaseous mobile phase? For gaseous mobile phase, here, for example, we are dealing with the GC, gas chromatography, and gas chromatography is used for volatile and sometimes semi-volatile substances. So in the gas chromatography, we have the column oven temperature. So oven temperature needs to be varied, and remember, when we increase the temperature, we are going to increase the speed at which gas particles of the mobile phase moves. So if the gas particles of the mobile phase move faster, it means that whatever is being carried by the gas particles mobile phase is also going to move faster. And it should not be too faster and it should not be too slower, because with those either too slower or too faster, it's going to lead us to have improper separation. So we need to optimize it such that the oven temperature is in a condition or a temperature at which it can give us a proper separation. And for the liquid mobile phases, like in liquid HPLC, higher performance liquid chromatography, we can change the solvent system. So we can use what is called either isocratic elution. In this case, we are going, by changing solvent system, we are going to use gradient elution. We are going to explain them there. So gradient elution, here the best is gradient elution, whereby, let's say, let me rub quickly of gradient elution. Okay, here we are changing the solvent system. We may start with, let's say, 90% hexane versus 10% DCM, and then we see that this one gives us this separation. Okay, let's say this gives us this separation, and then we're like, this is not proper separation. This is peak A, this is peak B, and then we change it into maybe 70% hexane to 30% DCM, and now we are seeing a peak separated this way, and we're like, it is not still much better. What if we take it maybe to 30% hexane and 70% DCM, and now our separation is now perfect. Okay, it's now perfect. So this is what we call changes in solvent system, meaning that we try to vary them. Or maybe, for example, we can now, instead of using hexane, we can use, let's say we use even 60% ethanol and 40% DCM, something like that. So by changing the solvent system, especially in gradient elution in HPLC, meaning that we are using different volumes of solvents to help us achieve proper separation. And when it comes to, okay, so for variation in the selectivity factor, remember the selectivity factor by definition is the ratio of the distribution constants of the more retained species compared or relative to distribution constants of the less retained species. And that is why we say then selectivity factor can be KB, the distribution constant of the most retained species, over distribution constants of the less retained species. So with the variation in selectivity factor, we can vary selectivity factor to help us achieve a better or optimize column resolution, and that one we can do it either through changing the composition of the mobile phase, just like we have explained in case of the in case of this second point, changing the column temperature, just like we have explained, changing the composition of the stationary phase, and also using special chemical effects, especially in the case of silanol groups, HPLC. This one we are going to look at it more in detail. We are going to look at HPLC. So this is how you can optimize column resolution so that you have a better separation that is going to give you or help you determine and identify the components within a mixture properly and interpret them well. Happens sometimes. Imagine you are running a GC, for example, and your peak looks like this in this scenario A, or you have a peak which just look like this. Okay, this is scenario B. So this problem is what we call general illusion problem. General illusion problem simply means that the problem that occurs during separation that results into improper separation of the analyte in the mixture. So you inject your sample in the GC, you run it, set the parameters, you run it, but at the end of the day, your chromatograms can either look at can be like A or B. So you end up asking yourself, what is really happening in this? What could be the problem? So this problem that you're seeing that is giving you an improper separation is what we call general illusion problem. So in this case, you run your GC experiment and you come up with a chromatogram which look, let's say for example in A. So let's say this is our analyte X and this is our Y. So then there's something, as analyst, you're like, no, this cannot give me, you can't identify something like this. So you need to come up with ways to solve this problem. And how are you going to solve it? You need now to go back into optimizing column resolution. So you need either to play around, manipulate the GC. It's either you can play around with the solvent phase, solvent system. Maybe you run, let's say you run 90 hexane and 10% of DCM, and then now your A now look like this. Okay, this is now your A, and you are still not comfortable, and then you change the solvent system maybe to 70% hexane and 30% DCM. So this is hexane, and now it comes into maybe this is still like this. So this is this one. Okay, and then you try it again and run it maybe 40% hexane and let's say 60% DCM, and now this one is now giving you a proper peak. So this is our X, Y, this is our X, Y, this is our X and Y. So you can see that just by changing the solvent system, you can have a good separation from whatever you started with here. So once you have general illusion, once you have noticed a general illusion problem in your chromatogram, then as an analyst, you need to play around with the parameters depending on which type of analysis are you running. Is it GC analysis or HPLC analysis? So for the liquid chromatography, the LC, you can vary the retention factor, which is K, can be done through gradient elution. And we have said gradient elution is when now you are changing the solvent system. You can start even from here. Let's say if it is not giving you a proper separation, you can then decide, okay, let me try hexane, a mixture of hexane, DCM, hexane and ethanol, hexane and ethanol, hexane and ethyl acetate, things like that, or DCM and methanol. So you just keep on varying or doing gradient elution, running with different solvent systems until you get a proper separation. And we have what is called also solvent programming, and you can also sometimes we have what is called isocratic elution. So let's say you are running it, you have tried, and then when you reach at 40%, 60%, you are now having a proper separation, and then you are now deciding, okay, in this column or in this GC I'm going to run it, or in this HPLC I'm going to run it with a solvent system of 40-60 throughout. So the difference between gradient elution and isocratic elution is that in gradient elution you run it with several solvent mixture or systems or percentage as you during the analysis, while in isocratic elution you run it with one solvent system throughout. So if you decide to run it, let's say with 80%, 20% DCM ethanol, then throughout the entire separation or throughout the entire analysis, then this is what we call isocratic elution. One solvent is used, one solvent system is used, unlike gradient elution in which you are going to have different solvent system through the entire analysis. In GC you can use the temperature programming whereby you have oven temperature. Oven temperature, maybe you set it at 70%, 70 degrees Celsius or 120 degrees Celsius, it depends. So that we are going to do much of this in GC. So because we have column temperature, oven temperature, detector temperature, the temperature of the least volatile, the temperature of the most volatile, we are going to look those. So temperature programming is whereby you increase temperature a little bit as you perform your analysis until the temperature that is going to give you a better column resolution. So general elution problem is just the problem that you encounter during the analysis that will give you a bad chromatogram, a chromatogram that does not give you a proper separation, does not give you a quality peaks. So what you need to do, in this case is that you need to change the solvent system. You need to use different temperatures until you achieve your goal, which is a proper separation of the peaks or better quality peaks. Yeah, test your understanding. You, based on what we did in slide 1, you can try it by applying that in this slide and you can do it. All right, this is for today. See you in our next class. We are going to start looking at GC. So there are things that we looked in the past video and this one. What is chromatography? What is stationary phase? What is mobile phase? Elution, eluent, eluate, if you remember those. And we look at theory of chromatography. We look at band broadening. We look at column elution, column efficiency. And we look at also factors contributing to band broadening or zone broadening and how band broadening affects column efficiency. We looked at those yesterday. We looked at terms like retention factor, distribution constant, selectivity factor, and also we looked at the Van Diemter equation, H is equal to AB over U term CU, and we looked at what each and everything means and how they contribute to band broadening and how they results into they affect column efficiency. And today we have looked at column resolution. So I hope this tutorial helped you in one way or the other. Remember to subscribe, share with your friends, and subscribe. Thank you. Bye.